This video is an introduction to assembly programming using the Arduino Uno. Microcontroller ATmega328 found on the Uno is also highlighted in terms of programmable registers and instruction set. So why assembly? Assembly code is optimized for speed and space. Assembly coding allows you to learn hardware organization of the microcontroller, and for the Arduino we learn more about the ATmega microcontrollers. Assembly code can take full advantage of the controller hardware features since the assembly program interacts directly with the architecture of the microcontroller. To program microcontroller ATmega328 in assembly, we need to be familiar with two things: the hardware organization of the microcontroller and the instruction set. Hardware knowledge includes programming the ports, and we have 3 ports for the microcontroller: ports B, C, and D. And also we need to be familiar with the programmable registers within the processor inside the microcontroller. In regards to the instruction set, we need to be familiar with different types of instructions. We have arithmetic and logic instructions, branch instructions, data transfer instructions, bit and bit test instructions, and control instructions. The memory map of the ATmega328 microcontroller is shown here. The first 32 bytes of memory are reserved for general purpose registers from R0 to R31. The memory locations or addresses for these general purpose registers start from location 00 hexadecimal all the way to location 1F hexadecimal. And these registers are split into 2 parts. From R0 to R15 is one part, and the second part is from R16 to R31, and they are split based on their functionality and usage within the instruction set of the microcontroller. Registers R0 to R25 are all 8-bit registers used to store 8-bit values. We can also store 16-bit values by using pair registers R26 and R27 to give us register X, where the low byte of the number is stored in R26 and the high byte is stored in R27. And register Y is represented by R28 and R29, and register Z R30 and R31. To perform assembly programming using the Arduino IDE, we need to create 2 files: the INO file, which will contain the C++ code, and the S file, which will contain the assembly code. These 2 files must have the same name and must exist in the same directory. Within the Arduino IDE, we first create the INO file, and then we come to this down arrow, click on it and select New Tab, and we name the tab here LED dot capital S. This is the S file. So now we have one tab is for the S file to store the assembly code, and the other tab is the INO file, which is used to store the C++ code. In this first example, we want to blink an LED connected to digital pin D12 of the Arduino Uno. So this part is the C code needed, and this part is the S file, which contains the assembly code. Inside the INO file, the first thing we want to do is to declare function prototypes which are external to the C code. These 2 functions will contain the assembly code needed, and they are both inside the S file of the program. Inside the S file, before we can start using these 2 functions here, we need to declare these 2 functions as global functions by using the global directive. We also need to define this macro here, which will define the IO space address, and we need to include this header file, which will allow us to access the ports and the programmable registers of the microcontroller. Inside setup, function start is called. The program will jump to the S file, and this is the start label of the function, and these are the contents of the function, the assembly contents. So the first thing we do using this assembly instruction is to set pin PB5, which is digital pin 12 of the Arduino, as output, and then return, which will return to the setup function. Inside the loop function, function LED is called, and the byte value of 1 is sent. And here within the S file we have this label for the function LED, and these are the assembly contents. The byte value here, 1, sent by the function call, is stored in this register R24 and compared with this byte value 0 using the CPI instruction compare immediate. If these two values are equal, then this instruction will be executed, which is branch on equal, and the program will jump to this label LED off. If the values are not equal, this instruction will be ignored, and this next instruction will be executed, which will set pin D12 located at port B to high. Next, the program will return to the loop function, and then the delay 200 millisecond will be executed. Function LED is called again, but this time we send a value of 0. And here inside the S file at label LED, the value of 0 is compared with this 0, which are equal, so this instruction will be executed, where the program will branch to label LED off. And here we will clear the bit at port PB5. It means we set pin D12 to low, and then we return to the function call, which is the loop function, and then we implement the delay 200 millisecond, and the process is repeated indefinitely, and we have blinking LED. In the second demonstration of the blinking LED, the delay between the blinks is now done as an assembly program within the S file, and here within the Iona file we'll just do function calls. So this function, when it is called and executed, it will set digital pin D12 as output, and then this function LED will be called, and the byte value of 1 is sent and stored in this register R24 and compared with 0, and they are not equal, so this instruction will be ignored, and digital pin D12 is set high, and then this function is called myDelay by using the opcode relative call. Subroutine myDelay uses a nested loop to implement the delay, where we have an outer loop and an inner loop. Register R20 is used to store the initial count value of the outer loop, while register pair R30 and R31 are used to store the 16-bit initial count value of the inner loop, where the low byte is stored in R30 and the high byte is stored in R31. Identifier delay value is defined by this directive here, and this is the initial count value of the inner loop. This instruction will do a 16-bit subtraction, where 1 is subtracted from the 16-bit value stored in R30 and R31, and then we check if the result of subtraction is non-zero. If so, then this instruction will be executed, where the program will jump to inner loop and we have a loop. The loop only exists when the subtraction leads to a 0, so this instruction will be ignored, and the next instruction will be executed, where the content of R20 is subtracted by 1, and if the result is non-zero, then the program will jump to outer loop and we have a loop, and the loop exits when the subtraction gives us a 0, and this instruction will be ignored, and the program will return to the calling subroutine, and the next instruction will be executed, which is a return, where the program will return to the loop function and then the next function call, and so on. More assembly programming using the Arduino platform will be presented in future videos. Thank you for watching.